Welcome to Homework Lib.
Hi, Randall. So, unfortunately, you're not giving me the table, but I'm going to tell you the general way to do it, and I'm going to do an example using benzoic acid, which has a pKa of 4.3. Okay, of 4.2 or 4.20. Okay, so the general procedure to generate a buffer is that you need to add the acid. I'm going to label it as AH and the conjugate base, which is going to be A minus, right? Another way that this is frequently found, sometimes they replace the A with a B just for making it clear that you're going to have the conjugate base and B minus it's going to be the base. So for example, in the case of benzoic acid, what you're going to have is you have your nice benzene ring and attached to a carboxylic acid. And the reaction that you're studying here is when you add this guy to water, what is going to happen is that you're going to generate H3O plus the conjugate base, that is the benzoate. So in order to have a buffer, you need to have a certain amount of this guy, of the conjugate base, and a certain amount of the associated acid. So the way to generate a buffer with a specific pH obeys the Henderson-Hasselbalch equation, right? Which tells us that the pH of a solution is going to be equal to the pKa plus the logarithm of the concentration of the base divided by the concentration of the acid. Okay? So for example, we want a target pH of 4.3. For every acid that you have on your table, you're going to plug in the value for the pKa. In this case, it is going to be 4.2. And this is equal to the logarithm of the concentration of B minus divided by the concentration of HB. Okay? So what you need to do is to solve for this ratio, because this ratio, it is going to tell us how much we can deviate from the actual pKa of our system, right? If the concentrations are the same, what is going to happen is that the pH is going to be equal to the pKa. So if you have an acid in your table that has a pKa of 4.3, you need to mix the same amount of the associated salt of the acid, which is going to contain the base, and the same amount of the acid, correct? So the way to get these ratios, we simply subtract one side by the other. So 0.1, it's equal to log of this ratio of concentrations, right? We are going to exponentiate with a base 10, and this is going to tell us that in this particular scenario, this is the ratio of concentrations that we need to obey. So for meaning that HB times 10 to the 0.1 needs to be equal to the concentration of B minus. Okay. So this is essentially 1.26 times that concentration. Okay. So now there are two ways to do it. The first one, you add a certain mass or more precisely an amount of mole of the acid that satisfies this condition. Let's say that you want to add, I don't know, 26 grams, for example. You transform that to mole and you just verify the amount of the conjugate base that you need to add. For example, in this case, I could add sodium benzoate in order to provide this B minus. Okay. Now, the other way to do it is add an amount of acid and then add enough strong base to deprotonate the acid. The acid, satisfying the condition that we implied before. You can do, for example, in this case, let's say that we want, I'm going to label this the HB directly as being my benzoic acid, and I'm adding a certain amount of OH minus, right? And this is going to generate H2O plus B minus. So the way to do it is you have an initial value. I'm going to label this N0 as being the amount of mole that you have, the amount of change that you are going to require. Remember that in this case, the final volume is going to be the same, so I can do the ice table in moles. I can also convert this in concentrations. So the amount that I need to add of OH minus, let's call it X, that is going to be consumed. The water doesn't matter, and of B minus, a plus X amount is going to be generated. So that means that at equilibrium, we're going to have N0 minus X, 0, and X. So that amount of mole, you can divide it by the final volume. This is going to give you the concentration of HB. You can do the same thing with the concentration of B minus. And you're going to realize that in the previous equation that we have, in the Henderson-Hasselbalch, equation, this is going to turn into pKa plus logarithm. The final volumes are going to cancel on both sides, and this becomes X divided by N0 minus X. Okay? And you just need to solve for X given a value of N0. So you can choose the amount of mole at the beginning that you're going to have, and X is going to be the amount of base that you need to add, amount of a strong base. So in that way that is another way that you can generate a buffer with a specific pH. Just to summarize this procedure, the final part is going to be pH equals pKa plus log of X divided by N0 minus X. Okay? So if this is 4.3, the pKa, I'm going to use the same example as before. Solving this equation would turn into 10 to the 0.1. It's going to be equal to X divided by N0 minus X. I can say if N0 is equal 1 mole, one minus X, 10 to the 0.1, it's equal to X. You solve this equation, and X is going to be the amount of mole of a strong base that needs to be added. Okay, so those are the two possible procedures that you have. and you can repeat it with all of the assets that you have on your table.